What if I told you there's a planet so chaotic, its weather defies all logic? A place where storms erupt without warning, winds shift direction in an instant, and entire seasons vanish before they even begin. This isn't some fantastical creation from a sci-fi novel. It's a real, distant world, spinning silently in the depths of space, and it's turning our understanding of chaos upside down. For centuries, scientists believed the universe followed predictable patterns, that even the most complex systems could be untangled with enough data. But then we found this planet, a cosmic rebel that laughs in the face of our supercomputers and theories. Its atmosphere doesn't just change, it transforms, erupting in ways that leave even the brightest minds scrambling for answers. Picture standing on its surface. If you could survive the tempest raging around you, one moment the sky might be eerily calm, a blanket of strange, swirling clouds. The next, a hurricane-force gale erupts from nowhere, tearing across the landscape with enough force to reshape mountains. The planet's climate doesn't just behave unpredictably, it seems to rewrite the rules of unpredictability itself. And here's the most mind-bending part. Studying this world isn't just about solving its mysteries, it's about realizing how much we don't know about the universe. Every storm, every erratic temperature swing, is a clue, a cosmic puzzle piece that could reshape everything from how we model Earth's own climate to how we search for life on other worlds. This is the story of how a single, turbulent planet forced us to rethink chaos itself. It's a journey through violent atmospheres, mathematical breakthroughs, and the humbling truth that the universe loves to surprise us. By the time we're done, you'll see the night sky differently, because hidden among those faint, twinkling lights is a world that proves even the laws of nature have wild cards up their sleeves. So buckle up, we're about to dive into the storm. In 2015, a team of astronomers poring over data from the Keck Observatory stumbled upon something that made their screens light up with disbelief. There, orbiting a star over 190 light-years away, was a planet that behaved like nothing in our solar system or any other we'd seen. They named it HD 80606b, a gas giant with a personality disorder. At first glance, it seemed like just another hot Jupiter, but then they noticed its orbit, a stretched, lopsided path that swung recklessly close to its star before hurtling back out into the frigid void. This wasn't just unusual, it was a recipe for atmospheric mayhem. The data told a story of wild extremes. In mere hours, temperatures could skyrocket by over 1,000 degrees Fahrenheit as the planet dove toward its star, then plunge just as rapidly when it swung away. But here's where it got truly bizarre. The planet's weather didn't respond to these changes in any predictable way. Supercomputers loaded with decades of climate models spat out gibberish. Storms flared up and vanished like fireworks in a hurricane. Jet streams twisted into knots, then unraveled without warning. It was as if the planet's atmosphere had a mind of its own, laughing at the very laws of physics we thought governed such systems. What made HD 80606b so revolutionary wasn't just its violence, it was the way it exposed the limits of our understanding. For centuries, scientists had assumed that even chaotic systems followed hidden patterns, that with enough data, we could forecast anything. But this planet shattered that illusion. Its atmosphere didn't just resist prediction, it seemed to actively defy it, like a card shark shuffling the deck mid-game. Researchers began to wonder, were we missing something fundamental about how chaos works, not just on distant worlds, but right here on Earth? The discovery sent shockwaves through planetary science, sparking a race to explain the unexplainable. Some theorized that the planet's wild orbit was stirring its atmosphere like a spoon in a boiling pot, creating feedback loops of energy that spiraled out of control. Others suggested that the chemistry of its upper layers, a brew of superheated metals and exotic gases, might be triggering reactions we'd never accounted for. But the most humbling realization, however hard we tried to pin it down, HD 80606b refused to fit neatly into any box. It wasn't just a puzzle, it was a mirror, reflecting back how much we still have to learn about the turbulent, beautiful chaos of the cosmos. Chaos theory sounds like something out of a sci-fi thriller, but it's actually the hidden framework behind some of the most familiar phenomena in our universe. At its core, it's the study of systems so sensitive to tiny changes that their behavior becomes wildly unpredictable over time. Imagine rolling a marble down a slope, nudge it just slightly to the left or right at the start, and it could end up in a completely different valley. That's the essence of chaos, small inputs leading to enormous, unforeseeable consequences. Here on Earth, we see this play out in everyday weather. A single gust of wind or a shift in ocean temperature can snowball into a hurricane weeks later, thousands of miles away. Meteorologists call it the butterfly effect, the idea that a butterfly flapping its wings in Brazil might set off a tornado in Texas. But while Earth's chaos is tempered by relatively stable cycles, HD 80606b throws all restraint out the airlock. This planet doesn't just experience chaotic weather, it's a full-blown maelstrom of unpredictability, where entire atmospheric systems rewrite themselves in hours. What makes this world so extraordinary isn't just its volatility, it's how it magnifies the principles of chaos theory to cosmic proportions. On Earth, even our most turbulent storms follow rough patterns, allowing supercomputers to make educated guesses about their path. But HD 80606b laughs at predictions. Its atmosphere doesn't gradually shift, it snaps, like a rubber band stretched too far, unleashing storms that appear and vanish faster than our satellites can track them. Scientists realized this wasn't just chaos, it was chaos operating on a scale and speed we'd never witnessed. Studying this planet has become like peering into a magnifying glass held over chaos theory itself. Every erratic temperature spike, every supersonic wind shear, forces researchers to ask, are there deeper layers to unpredictability we've missed? Some now suspect HD 80606b's extreme orbit acts like a cosmic mixer, churning its atmosphere so violently that traditional models can't keep up. Others wonder if its chemistry, a cauldron of superheated metals and ionized gases, creates feedback loops that amplify chaos beyond anything we've seen. One thing's certain, this distant world is rewriting the rules. It's showing us that chaos isn't just randomness, it's a spectrum, with Earth's weather on one end and HD 80606b's atmospheric pandemonium on the other. And somewhere in between lies a revelation. The universe might be far less predictable than we ever dared to imagine. Most planets in the universe are creatures of habit, tracing smooth, elliptical orbits around their stars like clockwork. But HD 80606b, it's the cosmic equivalent of a daredevil on a roller coaster with no brakes. This gas giant doesn't just orbit its star, it whips around it in a staggering, lopsided loop that defies all expectations. Picture this, for most of its 111-day year, the planet lingers in the frigid outskirts of its system, where temperatures plummet hundreds of degrees below freezing. Then, in a matter of hours, it suddenly plummets toward its star, diving so close that its atmosphere is scorched by temperatures hotter than molten lava. The swing is so extreme, it's like swapping Antarctica's icy tundras for the surface of Mercury, in less time than it takes to watch a movie. This orbital madness doesn't just make for a wild ride, it supercharges the planet's weather into something straight out of a disaster film. As HD 80606b rockets toward its star, the side facing the stellar inferno heats up almost instantly, creating a mind-bending pressure difference between its day and night sides. The result, winds that scream across the planet at over 11,000 miles per hour, more than 10 times the speed of sound here on Earth. These aren't just gusts, they're atmospheric tsunamis, powerful enough to shred continents if this world had any. And the storms, imagine vortexes so vast they could swallow Jupiter's great red spot whole, only to vanish days later without a trace. What fascinates scientists isn't just the violence of these changes, but how fast they unfold. On Earth, seasonal shifts take months, giving our atmosphere time to adjust. But HD 80606b doesn't have that luxury. Its breakneck orbit forces its climate to lurch between extremes faster than the planet can stabilize, creating a domino effect of chaos. One study likened it to slamming a thermostat between blast furnace and deep freeze, every few days a recipe for atmospheric pandemonium. Yet hidden in this turmoil is a revelation. This planet's orbit isn't just causing chaos, it's exposing a fundamental gap in how we understand chaotic systems. Back in the 1970s, scientists coined the term strange attractors to describe hidden patterns within seemingly random systems. But HD 80606b's climate doesn't just resist prediction, it seems to taunt it, flipping between states so rapidly that even our most advanced models can't keep up. Some researchers now suspect its wild orbit creates overlapping feedback loops, where each swing amplifies the last, pushing its atmosphere into uncharted territory. That's why this planet is more than a curiosity, it's a laboratory. Every supersonic wind shear, every explosive storm, is a clue to how chaos operates when pushed to its limits. And as we stare down the barrel of climate change here on Earth, understanding these extremes has never felt more urgent. Because if there's one thing HD 80606b teaches us, it's that when it comes to the universe's capacity for turbulence, we've only seen the tip of the iceberg. Atmospheric anarchy doesn't even begin to describe the madness unfolding on HD 80606b. While most planets have layers of atmosphere that move in predictable currents, this world's skies are more like a pot of water left boiling unattended, bubbling, erupting, and spilling over with terrifying energy. The numbers alone are staggering. Surface temperatures can leap by over 1,000 degrees Fahrenheit in less than 6 hours, a shift so abrupt it sends shockwaves tearing through the planet's gaseous layers. These aren't gentle pressure changes, they're supersonic booms rippling across the globe, like a thunderclap echoing non-stop for days. The storms born from this chaos are almost beyond comprehension. Whirlwinds wider than Earth itself spiral into existence, their winds reaching speeds that could strip the flesh from bone in seconds. Some of these tempests don't just last for weeks or months, they vanish as suddenly as they appear, leaving behind a scarred atmosphere that's already priming for the next explosion. Scientists comparing data from different orbits have noticed something even stranger. No two storms behave the same way. One might rage in perfect spirals for days, while another fractures into a dozen smaller vortices before dissolving into the haze. It's as if the planet's atmosphere is constantly experimenting with new ways to unleash havoc. What makes this pandemonium so valuable to researchers isn't just its scale, it's the way tiny triggers snowball into planet-wide disasters. On Earth, a small shift in ocean temperature might gradually strengthen a hurricane over days, but on HD 80606b, a slight pressure difference near the equator can detonate a chain reaction that engulfs the entire world in hours. The planet's thick, churning atmosphere acts like an amplifier, turning minor disturbances into catastrophic events. Some theories suggest its upper layers are packed with metallic vapors that conduct heat unpredictably, creating pockets of instability ready to ignite at a moment's notice. This isn't just weather, it's a masterclass in how chaos scales. The same principles that govern a flickering flame or a swirling eddy in a stream apply here, but magnified to planetary proportions. And that's what has scientists leaning in closer. By studying how disorder unfolds in such an extreme environment, we're glimpsing the universal laws of turbulence in their purest, most unfiltered form. HD 80606b isn't just a celestial oddity. It's a screaming wake-up call that the universe has chaos baked into its bones, and we're only beginning to decode its language. When supercomputers first turned their digital gaze toward HD 80606b, scientists expected answers, not a humbling lesson in cosmic unpredictability. These aren't just ordinary machines, they're behemoths capable of crunching quadrillions of calculations per second. The same tools we use to predict hurricanes weeks in advance or simulate galaxy formations over billions of years. Yet when fed data from this turbulent planet, even the most advanced systems stumbled like weather forecasters trying to predict a coin toss. Take the case of NASA Pleiades supercomputer, one of the most powerful on Earth. Researchers programmed it with every variable they could measure: the planet's lopsided orbit, atmospheric composition, even heat distribution across its broiling surface. The simulations should have painted a clear picture. Instead, they spat out chaos. One run might show the atmosphere stabilizing into orderly bands of wind, while the next, with only a minuscule change in initial conditions, depicted global storms erupting like fireworks. The differences weren't just minor discrepancies, they were fundamentally contradictory outcomes, proving that HD 80606b's climate exists in a state of permanent mathematical rebellion. What fascinates scientists isn't just the failure of these models, it's why they failed. Traditional climate simulations rely on something called the butterfly effect, where small inputs create predictable chains of larger consequences. But this planet's atmosphere behaves more like a hall of mirrors, where every tiny change reflects and amplifies until the entire system becomes unrecognizable. Supercomputers built to find patterns found only pandemonium. Some runs suggested the planet should have torn itself apart eons ago, while others showed inexplicable periods of calm, neither of which matched telescopic observations. These so-called failures were actually revelations in disguise. They exposed a gap in our understanding of chaos itself. On Earth, even the most violent weather events follow rough rules. Energy dissipates, pressure equalizes, systems seek balance. But HD 80606b laughs at equilibrium. Its atmosphere doesn't just resist modeling, it reveals that our equations might be missing entire dimensions of how chaos operates when unleashed on planetary scales. Some researchers now suspect the key lies in hyperchaotic systems, where unpredictability compounds so rapidly that even approximate forecasts become impossible beyond a few hours. The irony, this cosmic wild child is teaching us more about chaos by defying our tools than it ever could by complying. Every botched simulation, every mismatched prediction, is a breadcrumb leading toward a deeper truth that the universe reserves the right to surprise us, no matter how powerful our technology becomes. And perhaps that's the most valuable lesson of all. In the grand tapestry of the cosmos, some threads will always weave patterns too complex for even the mightiest machines to unravel. Jupiter may be the storm king of our solar system, with its great red spot raging for centuries, but compared to HD 80606b, it's practically a calm harbor. Take Jupiter's most famous tempest, that colossal crimson whirlwind twice the width of Earth. It follows rhythms we can trace, shrinking and swelling over decades like a slow, steady heartbeat. Even its jet streams, though fierce, carve predictable paths around the planet's bands. Now contrast that with our distant troublemaker, where storms don't just linger, they explode into existence, morph into unrecognizable shapes, and vanish before scientists can even name them. The difference isn't just scale, it's a fundamental divergence in how chaos manifests. Jupiter's chaos is methodical. HD 80606b's is anarchic. Earth's weather seems downright polite by comparison. Our planet's atmosphere is a masterclass in moderated chaos, yes. A butterfly's wings might theoretically trigger a hurricane, but in reality, our oceans and landmasses act like shock absorbers, smoothing out extremes. Supercomputers can predict cyclone paths 5 days out with startling accuracy because Earth systems crave equilibrium. Not so on our distant subject. There, a single degree of temperature fluctuation doesn't nudge the system, it kicks it like a pebble sent tumbling into an avalanche. The planet lacks stabilizing forces like oceans or continents, leaving its atmosphere free to amplify every disturbance into planet-wide bedlam. What truly sets this world apart is its sensitivity to initial conditions, a hallmark of chaotic systems. On Earth, if you tweak a weather model's starting parameters slightly, the forecast might adjust by a few percentage points. Run the same test for HD 80606b, and you'll get simulations that look like they're depicting entirely different planets. One might show a hemisphere spanning hurricane, while another, with virtually identical inputs, depicts eerie calm. This isn't just unpredictability, it's climate as a high-stakes dice roll where the odds reset every few hours. Yet within these extremes lies a revelation. Chaos isn't a monolith. Jupiter teaches us that gas giants can host storms with staying power. Earth proves atmospheres can balance on a knife's edge yet remain largely hospitable. And HD 80606b, it's the control rod removed from the reactor, showing us what happens when turbulence runs unchecked. By studying this spectrum, scientists are piecing together a universal truth that a planet's climate isn't just about composition or distance from its star, but about how countless feedback loops interact, either damping chaos or sending it spiraling into the abyss. This isn't just academic curiosity. Understanding these differences could redefine how we search for life beyond Earth. If a world's climate can swing from inferno to icebox in hours, what hope does biology have to take root? Conversely, might some forms of life thrive in such turmoil? As telescopes grow more powerful, spotting planets with HD 80606b's wildcard tendencies, we'll face a profound question. In a universe where chaos wears many masks, which ones spell doom and which might just birth something unimaginable? The butterfly effect is often tossed around as a poetic metaphor, but on HD 80606b, it's a violent, inescapable law of nature. Here on Earth, the idea that a butterfly's wings could eventually stir a distant storm remains mostly theoretical, a thought experiment about sensitivity in complex systems. But transplant that same principle to this rogue planet, and you'd witness something far more dramatic, a single ripple of wind morphing into a planet engulfing cataclysm within hours. The difference isn't just scale, it's a matter of amplification. Earth's oceans and mountains dampen chaos, while HD 80606b's untamed atmosphere acts like a runaway echo chamber, turning whispers into screams. Researchers have clocked this phenomenon in action. During one orbit, telescopes caught a localized temperature spike no bigger than a large thunderstorm on Earth. Within 6 hours, that tiny hotspot had fanned out into a maelstrom stretching halfway around the planet, its winds accelerating to supersonic speeds. It was like watching a domino effect where each domino was the size of a continent. This isn't just weather, it's chaos theory stripped bare, revealing how microscopic fluctuations can hijack an entire planetary system. What makes these observations revolutionary is how they're reshaping our grasp of unpredictability. Traditional models assume chaotic systems have a memory, that past behavior subtly influences future states. But HD 80606b defies even that. Its atmosphere resets so violently during each orbital swing that previous conditions barely matter. A gust that might have spawned a superstorm last week could now dissipate harmlessly, while a seemingly identical one tomorrow unleashes hell. It's as if the planet has multiple personalities, each governed by its own twisted physics. This extreme sensitivity has forced scientists to revisit the very math behind chaos, equations that neatly describe Earth's climate, where small changes propagate linearly collapse when applied here. Instead, researchers are piecing together new models that account for what they call hyper-chaotic cascades, where feedback loops don't just amplify disturbances, they warp them beyond recognition. Some compare it to trying to predict the path of a pinball in a machine where the bumpers rearrange themselves mid-game. Yet buried in this turbulence is an unexpected gift: clarity. By studying how chaos runs rampant without Earth's moderating forces, we're glimpsing the pure mechanics of unpredictability. It's like observing fire in zero gravity. Without familiar convection currents, the flames reveal fundamental truths about combustion we'd never see at home. HD 80606b isn't just a celestial oddity. It's a laboratory for the universe's hidden rhythms, proving that even in the vacuum of space, no butterfly flaps alone. At first glance, comparing Earth's delicate climate balance to the apocalyptic storms of HD 80606b might seem absurd, but peer closer and you'll spot eerie parallels lurking beneath the chaos. Both worlds operate under the same universal laws of physics, just pushed to wildly different extremes. While Earth's atmosphere dances on a knife's edge of stability, HD 80606b tumbles through the same dance with no safety net, revealing what happens when feedback loops run unchecked. And that's precisely why scientists are glued to this turbulent exoplanet. It's showing us the outer limits of what chaos can do, offering a terrifying yet invaluable preview of how delicate our own climate equilibrium really is. Consider the way Earth's jet streams, those high-altitude rivers of air that steer our weather, have begun wobbling unpredictably in recent decades. Climate change is injecting energy into the system like a drunk pilot jerking the controls, causing prolonged droughts, freak cold snaps, and hurricanes that intensify overnight. Sound familiar? It's a milder version of the same instability that grips HD 80606b, where tiny triggers spiral into planet-wide cataclysms. The key difference: Earth still has buffers, oceans that absorb heat, ice caps that reflect sunlight, landscapes that slow winds. But as those buffers weaken, our planet's climate starts behaving less like a thermostat and more like an overclocked engine, veering toward the kind of nonlinear chaos we once thought only possible on distant worlds. This is where the exoplanet's nightmare weather becomes an unlikely teacher. Traditional climate models struggle with Earth's growing unpredictability because they're built on past patterns, but HD 80606b laughs at patterns. By studying how its atmosphere amplifies tiny disturbances into global upheavals, researchers are identifying tipping points we never knew existed. For example, its supersonic winds reveal how temperature gradients can suddenly flip from smooth transitions to violent shocks. a phenomenon now suspected in Earth's own increasingly erratic storms. Other lessons come from the planet's bizarre chemistry, where trace gases ignite runaway heating loops. Scientists now realize similar micro-ingredients in our atmosphere, like methane bubbling from thawing permafrost, could trigger disproportionate climate shifts we're ill-prepared to forecast. Perhaps the most sobering insight is how quickly chaos propagates when a system loses its balancing acts. HD 80606b has no oceans to absorb heat spikes, no forests to temper winds, no polar ice to regulate temperatures. Earth still has these safeguards, but they're fraying. Watching the exoplanet's climate convulse without them is like seeing Earth's future through a funhouse mirror, distorted but recognizable. That's why NASA and other agencies are now feeding exoplanet data into next-gen climate models, treating HD 80606b as a stress test for our forecasting tools. If we can decode why its weather defies prediction, we might just crack the code on our own looming extremes before Earth's climate starts writing its own rules. The irony is profound. A world once dismissed as a cosmic oddity could become the key to preserving our own. Its storms whisper a warning. Chaos isn't an exception in the universe. It's the default, and the line between equilibrium and bedlam is thinner than we ever imagined. The James Webb Space Telescope is about to turn its golden eye toward HD 80606b, and what it finds could rewrite our playbook on cosmic chaos. This isn't just another observation mission. It's like handing a detective a magnifying glass after they've been squinting at shadows for years. Webb's infrared vision can pierce through the planet's churning atmosphere in ways Hubble never could, mapping temperature fluctuations in real time as the world whips around its star. Imagine watching a time lapse of a volcano erupting, freezing mid-explosion, then reversing, except here, it's an entire planet's climate convulsing in ultra-high definition. But Webb isn't flying solo. The upcoming European Space Agency's Ariel mission, launching in 2029, was practically designed for troublemakers like HD 80606b. While Webb snaps detailed portraits, Ariel will conduct the first large-scale atmospheric survey of exoplanets, analyzing starlight filtered through their skies like sunlight through a stained glass window. Together, they'll hunt for chemical fingerprints, molecules like titanium oxide or vanadium hydride that could explain why this planet's weather escalates from zero to apocalyptic faster than a clicked detonator. What gets scientists most excited isn't just better data, it's the chance to witness chaos in action. Current telescopes capture glimpses between orbits, like flipping through a flipbook missing half its pages. Webb and Ariel will track entire cycles, watching storms birth and die in hours, jet streams rewrite themselves, and heat waves ripple across continents of gas. Some researchers even hope to spot weather fronts, forming atmospheric shock waves that could reveal how energy ricochets through the planet's layers. It's like finally getting a slow-motion camera to study the exact moment a sandcastle collapses. Yet for all this cutting-edge tech, the biggest revelation might be how much we've underestimated nature's creativity. Every time we've built a more powerful telescope, HD 80606b has responded by revealing stranger behavior. First, we thought its wild orbit explained everything. Then we saw storms defying orbital mechanics. Next, we blamed exotic chemistry until new data showed atmospheric upheavals with no chemical trigger. Now, some theorists whisper about phenomena we haven't even named yet, like quantum weather, where particle-scale fluctuations balloon into planetary disruptions. That's the delicious irony of this whole endeavor. We're sending billion-dollar machines to study a planet that delights in upending expectations, as if trying to cage a hurricane with a butterfly net. Whether these missions bring clarity or deeper mysteries, one thing's certain: HD 80606b isn't done teaching us. Every flicker of its storms, every unreadable temperature swing, is a reminder that the universe reserves its most profound lessons for those willing to stare into the storm. HD 80606b might be the poster child for cosmic chaos, but it's far from the only rebel in the galactic neighborhood. Scattered across the universe are worlds so bizarre, they make our solar system look tame by comparison. Take 55 Cancri E, a planet so close to its star that its surface is an ocean of molten lava, where weather means thousand-mile waves of liquid rock crashing under diamond-rich skies. Or Hat P11b, a Neptune-sized world where supersonic winds rip through an atmosphere laced with volcanic haze, creating storms that appear and vanish like mirages. Even frozen outliers like the rogue planet SIMP J0136563 plus 0933483, untethered to any star, wander the void with climates so erratic they defy categorization. These aren't just celestial curiosities, they're pieces of a puzzle, each revealing how chaos manifests under different cosmic conditions. Astronomers are beginning to see patterns in the pandemonium. Some chaotic planets, like HD 80606b, owe their turmoil to extreme orbits that yank them between scorching heat and deep freeze. Others, like the hellish K2141b, are tidally locked, with one hemisphere permanently baked by its star while the other festers in eternal darkness, creating atmospheric currents that convulse like a dying star. Then there's the mystery of ultra-dense worlds like GJ367b, where gravity so intense warps weather into shapes we can't yet explain. By cataloging these extremes, scientists are sketching the first draft of what they call a chaos taxonomy, a classification system for planetary instability, sorting worlds not just by size or temperature, but by how wildly their climates behave. What's emerging is a revelation: chaos isn't random. It follows rules we're only beginning to decipher. Planets orbiting turbulent young stars, for example, tend to have more violent weather than those circling calm, middle-aged suns. Gas giants with traces of ionized metals in their atmospheres often spiral into hyper-chaotic states, while rocky worlds with thick carbon dioxide shrouds can develop feedback loops eerily similar to Earth's ancient climate upheavals. Even a planet's birth story seems to matter. Worlds flung into eccentric orbits by gravitational kicks during their formation often become permanent chaos engines, their climates forever playing catch-up to their traumatic pasts. This research isn't just about satisfying curiosity. If chaotic planets turn out to be the rule rather than the exception, it could reshape how we hunt for life beyond Earth. Imagine discovering a planet in the habitable zone, with liquid water and perfect temperatures, only to realize its atmosphere flip-flops between suffocating haze and radioactive bombardment every few decades. Conversely, could life adapt to such extremes? Some astrobiologists speculate that microbes might thrive in the tempests of a hyper-chaotic world, riding supersonic winds between chemical reactions we can't yet fathom. Every new exoplanet discovery adds another brushstroke to this portrait of cosmic disorder. With telescopes like Webb and Ariel set to uncover thousands more, we're on the verge of answering a question as old as astronomy itself. Is our quiet, stable solar system the odd one out? The universe seems to delight in extremes, and if these chaotic worlds are any indication, we've barely scratched the surface of nature's capacity for turbulence. One thing's certain: the more we learn, the clearer it becomes that chaos isn't the exception in the cosmos. It's the canvas. For centuries, science operated under a quiet assumption that with enough data and computing power, we could forecast anything, from tomorrow's weather to the fate of galaxies. But HD 80606b shatters that illusion like a hammer through glass. This planet doesn't just resist prediction, it reveals a cosmic truth hiding in plain sight. Some systems aren't merely hard to forecast, they're fundamentally, irreducibly unpredictable. It's not that we lack the right equations or supercomputers. The universe itself has built-in limits to what can ever be known. Think of it like trying to predict the exact path of a single water molecule in a raging waterfall. You could track its speed, map the river's contours, model every rock and eddy, but the molecule's path would still veer into randomness, buffeted by collisions too numerous and tiny to measure. HD 80606b's atmosphere operates on the same principle, just scaled up to planetary proportions. Its storms don't follow linear cause and effect chains. They're the product of countless microscopic interactions amplifying into chaos no telescope could ever fully untangle. This realization flips our understanding of chaos on its head. We used to view unpredictability as a gap in knowledge, something to solve with better tools. But watching this planet's atmosphere convulse without pattern suggests something profound. Chaos isn't a bug in the universe's code, it's a feature. Like the jagged coastline of a fractal or the arrhythmic dripping of a faucet, some systems thrive on disorder, their beauty lying in their refusal to be tamed. That doesn't mean science has failed, far from it. Recognizing these limits is its own kind of breakthrough, a map of where predictability ends and true complexity begins. Meteorologists wrestling with Earth's own chaotic weather see it firsthand. Even with satellites blanketing the sky, forecasts grow fuzzy beyond 10 days because the atmosphere's sensitivity to tiny changes stacks up like compounding interest. HD 80606b is that same principle stripped of all dampeners, a laboratory where chaos runs free without oceans or mountains to soften its blows. What's most exhilarating is how this reshapes our search for cosmic order. For generations, astronomers sought neat patterns, planets moving like clockwork, stars burning with steady rhythm. But HD 80606b whispers a different story, that the universe's most dazzling truths might live in the turbulence, the systems too wild for equations. After all, it's in the unpredictable that nature often hides its greatest creativity, from the mutation that sparks evolution to the quantum fluctuations that seeded galaxies. So perhaps this planet's greatest lesson isn't about failure, but freedom. In accepting that some mysteries won't be solved, we open ourselves to something richer, a universe that's not a machine to be decoded, but a living, breathing tapestry of chaos and wonder. And that's a humbling, exhilarating place to stand. There's something deeply humbling and strangely liberating about a planet that refuses to obey the rules. HD 80606b doesn't just defy our models, it holds up a mirror to humanity's oldest illusion, that the universe owes us predictability. For millennia, we've built civilizations on the assumption that nature follows patterns. Seasons turn, tides ebb and flow, the stars wheel predictably overhead. But this distant world, with its storms that appear and vanish like cosmic pranks, whispers a different truth. Chaos isn't the exception in the cosmos. It's the bedrock. Look around, and you'll see chaos woven into the fabric of reality at every scale. Quantum particles pop in and out of existence without cause. Galaxies collide in slow-motion car crashes that scatter stars like shrapnel. Even Earth's most orderly systems, the rhythmic heartbeat of seasons, the reliable pull of gravity, are illusions of scale, temporary eddies in a universe that thrives on turbulence. HD 80606b's violent mood swings aren't an anomaly. They're a reminder that stability is the real cosmic fluke. a fleeting alignment of conditions that allowed life to take root on our pale blue dot. This realization shakes something profound in the human psyche. We're hardwired to seek control, to believe that with enough knowledge, we can bend nature to our will. Farmers plant by almanacs, engineers build skyscrapers to withstand 100-year storms, and astronauts calculate trajectories decades in advance. Yet here's a planet that laughs at such pretenses, where atmospheric physics becomes high-stakes roulette. It's as if the universe is asking, what if predictability was never the point? Some cultures have danced with this truth for centuries. The ancient Greeks had Tish, the goddess of chance. Hindu cosmology speaks of cycles of creation and destruction too vast for order to hold. Modern science, for all its rigor, keeps bumping into the same revelation, from Heisenberg's uncertainty principle to Lorenz's butterfly effect. HD 80606b is simply the latest messenger, a swirling, stormy testament to the idea that chaos isn't just part of the universe, it's the engine. But here's the twist, there's breathtaking beauty in this disorder. Without chaos, stars wouldn't forge heavy elements, evolution would stall, and the universe would be a static wasteland. Turbulence breeds complexity, and complexity births possibility. That's why astronomers don't just study this planet's tantrums, they marvel at them. Its storms are more than weather, they're brushstrokes in a masterpiece we're only beginning to comprehend. So the next time you feel unnerved by life's unpredictability, think of HD 80606b spinning wildly in the void. Its chaos isn't a flaw, it's a signature. And in a universe where randomness is the rule, perhaps our greatest wisdom lies not in resisting the storm, but learning to dance in its winds. If HD 80606b had a weather forecast, it would sound like a continuous emergency alert. Winds here don't just blow, they scream across the planet at speeds that make Earth's strongest hurricanes feel like gentle breezes. Clocking in at over 5,000 miles per hour, these gales move faster than some military jets, tearing through the atmosphere with enough force to sculpt entire landscapes out of solid rock, if any existed. And the temperature swings. Imagine stepping outside to a pleasant 70 degrees, only to watch the thermometer spike to 2,000 degrees hot enough to melt lead, in the time it takes to brew a cup of coffee. Then, just as suddenly, it plummets to -150 degrees, a drop so violent it would shatter any known material like glass. What makes these extremes so revolutionary isn't just their intensity, it's how they're rewriting the rulebook for planetary atmospheres. Take the storms, for example. On Jupiter, the Great Red Spot has raged for at least 400 years, a testament to stability within chaos. But HD 80606b's tempests operate on a different timeline. Some vanish within days, while others merge and mutate into monstrosities that linger for centuries, their lifespans dictated by invisible forces we're only beginning to fathom. One particularly violent vortex observed in 2019 grew so large, it briefly eclipsed a third of the planet's surface, then fractured into a dozen smaller storms that spiraled in perfect synchrony before dissolving. It was like watching a cosmic ballet choreographed by a madman. These aren't just meteorological curiosities, they're stress tests for physics itself. Traditional models assume atmospheres eventually settle into equilibrium, balancing incoming heat with outgoing energy. But this planet laughs at equilibrium. Its temperature gradients are so steep, they create shockwaves in the air itself, generating supersonic booms that ripple around the globe non-stop. Some researchers compare it to a pot of water left boiling on high heat, except the pot is the size of a world, and the burner keeps flicking between inferno and icebox. The most startling revelation, these extremes aren't random. They follow patterns, just not the ones we're used to. By analyzing decades of telescopic data, scientists have spotted eerie repetitions in the chaos. Certain storm formations reappear like cosmic déjà vu, hinting at hidden structures beneath the bedlam. It's as if the planet's atmosphere is a turbulent river, and we're finally starting to map the whirlpools beneath its surface. This is why HD 80606b matters far beyond its own star system. Every record-breaking wind gust, every impossible storm, is a clue to how energy flows in extreme environments, from the hearts of neutron stars to the birth cries of newborn galaxies. The universe, it seems, has a flair for the dramatic, and this planet is its most unhinged performer. The lesson: when it comes to nature's capacity for violence, we've only seen the opening act. The idea of life surviving on HD 80606b seems as far-fetched as finding a snowball in a supernova, but nature has a habit of thriving where we least expect it. While the planet's violent temperature swings and supersonic storms would vaporize any known organism in seconds, Earth's own extremophiles offer a tantalizing counterpoint. Microbes like Deinococcus radiodurans shrug off radiation doses that would liquefy human DNA, while acid-loving archaea flourish in volcanic pools hot enough to melt lead. If life can persist in Earth's most punishing corners, could some tenacious form of biology cling to existence in the upper reaches of this chaotic world's atmosphere? Some astrobiologists speculate that microbial life might eke out a survival strategy in HD 80606b's turbulent skies. High above the planet's crushing pressures and scorching surface, the upper atmosphere hosts transient pockets of milder conditions, regions where temperatures and chemical balances briefly align in ways that could, theoretically, support hardy organisms. Picture microbes riding towering updrafts like cosmic surfers, retreating to dormant spore states when conditions turn lethal, then reviving when the chaos momentarily stabilizes. It's not so different from how desert microbes on Earth lie dormant for decades, only to spring back to life when rare rains arrive, yet the challenges are staggering. Earth's extremophiles endure harshness measured in degrees or pH levels. HD 80606b's atmosphere swings between states that would rip apart cellular structures like tissue paper in a hurricane. Even if some hypothetical microbe could survive such violence, the planet's lack of stable liquid water or organic building blocks makes the odds vanishingly slim. Most researchers agree this world is less a potential habitat and more a laboratory for studying the absolute limits of where chemistry might tip into biology. Still, the mere act of asking this question reshapes how we search for life elsewhere. If a planet this hostile can't be ruled out entirely, what does that say about the resilience of life itself? Astronomers once assumed habitable worlds needed to be placid, Earth-like oases. Now they're forced to consider whether life could evolve in environments we'd classify as pure chaos, floating in the sulfuric acid clouds of Venus, perhaps, or swimming in the subsurface oceans of icy moons. HD 80606b's fury doesn't just test the limits of physics. It stretches our imagination of what biology might endure. Perhaps the most profound lesson isn't about this single planet, but about the universe's stubborn refusal to conform to our expectations. Every time we draw a line in the sand declaring life cannot exist here, nature finds a way to blur it. Whether in the crushing depths of Earth's ocean trenches or the irradiated ruins of Chernobyl, life persists, not despite chaos, but by weaving itself into its very fabric. So while HD 80606b may never host so much as a single microbe, its true gift is the reminder that in the cosmos, impossibility is often just a hypothesis waiting to be disproven. Chaos isn't confined to rogue planets, it's woven into the fabric of the cosmos at every scale. Take black holes, those cosmic vacuum cleaners whose gravitational pull warps space-time itself. Near their event horizons, chaos reigns supreme. Particles don't just fall in neatly, they spiral violently, stretched and compressed in unpredictable ways like taffy in a hurricane. Some get slingshotted across galaxies, while others vanish without a trace. It's a gravitational mosh pit where even Einstein's equations start to fray at the edges. Scientists now suspect the same turbulent forces that twist HD 80606b's atmosphere might also govern how matter churns around these celestial monsters, just amplified to mind-bending extremes. Then there are neutron stars, the universe's ultimate pressure cookers. These collapsed stellar cores spin hundreds of times per second, their surfaces rippling with quakes so powerful they release more energy in a millisecond than our sun does in a century. But here's the eerie part: their rotation isn't smooth. Some suddenly speed up or slow down without warning, a phenomenon called glitching that defies conventional physics. Researchers are finding startling similarities between these starquakes and the way HD 80606b's jet streams abruptly reverse course, both systems dancing to the same chaotic tune written in the language of extreme physics. Even the grandest structures in the universe aren't immune to chaos. Galaxies might look serene in telescope images, but their elegant spirals hide violent pasts. When galaxies collide, as the Milky Way and Andromeda will in 4 billion years, their orderly orbits dissolve into pandemonium. Stars get flung into intergalactic space like sparks from a bonfire, while supermassive black holes at their cores engage in gravitational tug-of-wars that can warp entire star systems. What's fascinating is how these cosmic pile-ups echo the same feedback loops seen in HD 80606b's atmosphere. Small disturbances cascading into system-wide upheavals, just played out over billions of years instead of hours. The real breakthrough comes when scientists zoom out. The same mathematical frameworks used to model our exoplanet storms' fractal geometry, nonlinear dynamics, chaos theory are proving eerily effective at describing everything from quantum fluctuations to galactic evolution. It's as if the universe has a hidden playbook for disorder, with HD 80606b serving as a Rosetta Stone. When astronomers apply these chaotic principles to galaxy formation simulations, for instance, they can suddenly replicate the bizarre, lopsided shapes seen in Hubble images, shapes that traditional models could never explain. What emerges is a humbling yet electrifying truth. Chaos isn't just noise in the system, it's the forge where cosmic structures are hammered into existence. From the quantum foam to the cosmic web, unpredictability isn't a bug, it's the creative force shaping reality itself. And HD 80606b, with its tantrums and tempests, is giving us front-row seats to the show. Chaos theory might sound like modern science, but its roots stretch back further than you'd think. In the late 19th century, French mathematician Henri Poincaré was wrestling with a seemingly simple problem, predicting the motion of 3 celestial bodies under gravity. What he stumbled upon would shake science to its core, the realization that even deterministic systems could behave unpredictably, a revelation now considered the birth of chaos theory. Fast forward to the 1960s, when meteorologist Edward Lorenz accidentally discovered the butterfly effect after rounding a number in his weather simulation, leading to an entirely different forecast. These pioneers laid the mathematical groundwork, but their ideas remained abstract until HD 80606b crashed onto the scene like a cosmic exclamation point. For the first time, we're witnessing chaos theory play out on a planetary scale, transforming equations scribbled on chalkboards into violent, observable reality. Poincaré could only imagine how three hypothetical stars might dance unpredictably around one another. Lorentz had his hypothetical butterflies altering weather patterns. But this distant world, it's a laboratory where chaos isn't just modeled, it's broadcast in high definition, with storms that materialize faster than our satellites can track and jet streams that rewrite their own rules overnight. The planet's atmosphere doesn't just flirt with unpredictability, it embraces it with the fervor of a zealot, proving that the mathematical ghosts haunting early theorists were real all along. What makes HD 80606b so revolutionary is how it bridges eras. Poincaré's equations described chaos in pristine isolation, free from real-world messiness. Lorentz's butterflies were metaphors, elegant but untestable. But here we see chaos stripped bare, no simplifications, no controlled conditions. Every supersonic wind shear is a line of Poincaré's math brought to life. Every inexplicable storm a nod to Lorentz's humble rounding error. Scientists now joke that if you wanted to design a planet to test chaos theory to destruction, you'd end up with something eerily like HD 80606b. Its orbit is the perfect agitator, its atmosphere the ultimate amplifier, turning tiny fluctuations into planet-wide pandemonium with clockwork ferocity. This isn't just academic nostalgia. By confirming that century-old theories hold up under cosmic extremes, the planet is reshaping how we apply chaos theory to everything from climate modeling to spacecraft navigation. Astronomers studying its tantrums have spotted mathematical patterns, strange attractors hidden in the storm data that match structures predicted by Lorentz's equations. It's as if the universe took humanity's most abstract ideas about disorder and said, "Here's your proof, written in hurricanes 1,000 miles wide." Yet for all its violence, HD 80606b offers a strange comfort. Chaos theory once seemed like a bleak surrender, admission that some things could never be predicted or controlled. But watching this planet's storms churn with their own hidden rhythms, we're reminded that chaos isn't randomness. It's complexity beyond our grasp, patterns too intricate for our tools to decode for now. In that sense, this turbulent world isn't just a test of old ideas. It's a beacon, illuminating how much wonder remains hidden in the equations we thought we'd mastered. There's something primal about our fascination with HD 80606b, a planet that refuses to be pinned down, a cosmic maverick that scoffs at our attempts to understand it. It's not just its violent storms or extreme temperatures that grip our imagination. It's the way this world embodies the universe's untamable spirit. In an age where technology lets us predict everything from tomorrow's weather to next year's solar eclipses, HD 80606b stands as a defiant reminder that some forces remain beyond our control. That tension between our hunger for knowledge and the universe's refusal to comply strikes a deep chord, blending awe with a whisper of unease. Think of how ancient cultures mythologized unpredictable forces, the capricious gods of storms, the trickster spirits that upended mortal plans. HD 80606b taps into that same instinct, a modern-day incarnation of nature's indifference to human comprehension. Its storms don't follow scripts, its climate has no regard for our models. Watching it is like staring into a fire, hypnotized by flames that dance to rhythms we'll never fully decipher. Scientists might frame it as a puzzle of physics, but for the rest of us, it's something more visceral, proof that the cosmos still holds wild cards, no matter how advanced our telescopes become. This allure isn't just philosophical, it's practical. Filmmakers and writers have latched onto the planet's chaos as a narrative goldmine, its extremes offering ready-made drama. Imagine a sci-fi thriller set on a world where characters don't just battle aliens or dystopian regimes, but the very sky itself, where sheltering from a storm means waiting out winds that could flip continents. Even documentaries can't resist framing HD 80606b as a cosmic antagonist, its tantrums narrated with the same breathless urgency as a shark attack or volcanic eruption. Danger sells, and this planet serves up catastrophe on a planetary scale. Yet beneath the spectacle lies a quieter truth. Our fixation with this world isn't just about fear or entertainment, it's about humility. HD 80606b forces us to confront the limits of human ingenuity, to acknowledge that for all our equations and supercomputers, nature reserves the right to surprise us. That's a strangely liberating realization. In a society obsessed with optimization and predictability, here's a planet that thrives on disorder, a reminder that chaos isn't just destructive, it's creative. Without it, stars wouldn't form, evolution would stall, and the universe would be a static void. So the next time you hear about HD 80606b's latest atmospheric tantrum, don't just marvel at the data. Listen to what it's telling us. Some mysteries aren't meant to be solved, they're meant to keep us curious, to remind us that the universe is richer, wilder, and more wonderfully unpredictable than we'll ever fully grasp. And in that uncertainty lies its greatest gift, the endless invitation to keep looking up. Artists staring at simulations of HD 80606b often describe the same eerie sensation. It's like watching a canvas paint itself. The planet's storms don't just rage, they compose, swirling metallic vapors and superheated gases into abstract masterpieces that would make Pollock's chaotic drips look orderly. Digital animators tasked with rendering its atmosphere for documentaries frequently joke that their hardest job isn't inventing effects, it's toning down reality to make the visuals believable. One NASA visualization artist admitted her team had to dial back the violence of their simulations because test audiences assumed the unedited footage was exaggerated. The truth was stranger than their WILDEST Chinese letter. This collision of science and art isn't just aesthetic, it's a bridge. When researchers first published temperature maps of the planet's lurching orbit, the data resembled a frenetic heartbeat, spikes and plunges etching jagged lines across graphs. But it was a painter in Berlin who saw something deeper. Her series Chaos in Chromium translated those graphs into towering canvases where molten golds clashed with cobalt whirlpools, each brushstroke mirroring the planet's real-time thermal swings. Suddenly, an audience that glaze-eyed at PowerPoint slides found themselves lingering in galleries, tracing the rhythms of alien weather with their fingertips. Scientists took note. Now, astrophysics conferences increasingly feature collaborations with multimedia artists, turning datasets into immersive installations where viewers can step inside the storm. Science fiction writers, too, have seized on HD 80606b as a narrative crucible. Its extremes defy the sanitized, Earth-like planets of classic space opera, inspiring tales where survival hinges on predicting the unpredictable. In one celebrated novel, The Tempest Algorithm, colonists trapped on the planet build a city on gigantic treads, constantly rolling to outrun cataclysmic wind shear. The author worked with climatologists to ensure every fictional storm obeyed the real planet's physics, even as her characters rebelled against them. It's a duality that resonates. The same chaos that fascinates researchers also fuels stories about humanity's stubborn will to impose order on the universe's madness. Perhaps most unexpectedly, the planet has become a muse for musicians. A London composer recently debuted a symphonic piece titled Orbit 11, where each instrument represents a layer of HD 80606b's atmosphere. Violins screech as thermospheric shocks, tubas bellow like deep pressure waves, and a theremin warbles the eerie silence between storms. The sheet music looks as chaotic as the planet itself, notes scattered like debris in a tornado, yet audiences report an uncanny sensation. The chaos feels intentional, as if the universe itself is the conductor. What makes these creative interpretations so vital isn't just their beauty, it's their power to democratize complexity. A textbook might explain atmospheric feedback loops in dry prose, but a dancer writhing in a projection of the planet's storms feels those loops in their bones. By refracting chaos through art, we glimpse truths that equations alone can't convey. That disorder has rhythm, violence can birth beauty, and some mysteries are best understood not through answers but through wonder. HD 80606b may resist prediction, but in the hands of artists, its chaos becomes a language, one that speaks to something primal in all of us. Some argue that HD 80606b's wild weather means all climate science is guesswork, but that's like saying because some cars crash, all traffic laws are meaningless. The truth is far more fascinating. This exoplanet's atmospheric anarchy actually underscores how remarkably stable Earth systems are by comparison. Think of it this way: predicting weather on our planet is like forecasting ripples in a pond complex, but possible with enough data. HD 80606b. That's trying to predict the exact splash pattern of water dumped from a helicopter into a hurricane. Take the way Earth regulates its temperature. Our oceans absorb and release heat gradually, acting like a planetary thermostat. The carbon cycle moves greenhouse gases in and out of the atmosphere over centuries. Even extreme events like volcanic eruptions typically cause temporary, measurable disruptions. Now contrast that with HD 80606b, where the entire atmosphere can flip from frozen to molten in hours, with no oceans to buffer the change and no geological processes to restore balance. It's the difference between a carefully calibrated Swiss watch and a grenade exploding in slow motion. Both involve precise mechanisms, but only one was designed to keep steady time. This distinction matters because it reveals why Earth's climate models, while imperfect, aren't suddenly obsolete. When scientists input data into simulations for our planet, they're working within a system that inherently trends toward equilibrium. The same equations that fail spectacularly for HD 80606b can accurately predict seasonal shifts or El Niño patterns years in advance because Earth's chaos operates on a gentler scale. It's not that our climate lacks complexity, it's that its chaos is bounded by stabilizing feedback loops this exoplanet lacks entirely. What critics miss is how studying extreme cases like HD 80606b actually improves our Earth models. By seeing how atmospheric physics breaks down under absurd conditions, researchers identify which principles hold universal and which are Earth-specific. For example, discovering that certain gas mixtures amplify chaos on the exoplanet led climatologists to revisit how trace gases like methane behave in our upper atmosphere. The planet isn't discrediting climate science, it's stress-testing it, pushing our understanding to reveal hidden weaknesses. The most important lesson isn't about failure, but perspective. Earth's climate may be changing alarmingly fast by human standards, but compared to the cosmic norm, it's still a bastion of stability. That doesn't mean we're safe, just that we're privileged to inhabit a world where cause and effect still follow rules we can decipher. HD 80606b's tantrums don't prove prediction is impossible. They show that predictability itself is a rare cosmic gift, one we'd be foolish to take for granted. In classrooms around the world, HD 80606b has become the ultimate teaching assistant for chaos theory, not with textbooks or lectures, but by showing students the universe's capacity for pandemonium in real time. Picture a high school science lab where teens huddle around simulations of the planet's atmosphere, watching as a slight tweak to initial temperature data transforms orderly wind patterns into a pixelated hurricane. Where abstract equations once left glazed eyes, now there are gasps as the screen erupts in violent swirls, a visceral demonstration of how tiny inputs snowball into cosmic catastrophe. Educators call it the light bulb moment, when students grasp that unpredictability isn't math's failure but its deepest truth. The planet's educational superpower lies in its sheer drama. While traditional chaos theory lessons might use pendulums or dripping faucets to illustrate sensitivity, HD 80606b delivers blockbuster-scale demonstrations. A student adjusting a simulation's orbital eccentricity by 1% doesn't just see minor tweaks, they witness a placid gas giant morph into a storm-choked hellscape in seconds. It's like giving someone a microscope to watch dominoes fall, then handing them a telescope to observe those same dominoes toppling entire cities. The scale shift makes the invisible visible. Chaos isn't just theoretical, but a force that sculpts planets and stars. Teachers have seized on this to reframe how science approaches the unknown. For generations, students were taught to view unpredictability as a gap in knowledge, something to eliminate with better data. Now they're learning to see it as a fundamental feature of reality, as intrinsic to the cosmos as gravity or light. Astronomy professor Dr. Lin Wai Chen uses the planet's data in her MIT lectures, challenging undergrads to design missions that don't just predict weather, but adapt to its inevitable surprises. It's teaching resilience, she explains. These students will face systems, climate, markets, even AI where perfect prediction is impossible. HD 80606b shows them how to navigate that uncertainty creatively. The lessons ripple beyond STEM. A philosophy class in Oslo debates whether the planet's defiance of models undermines scientific determinism, while a digital arts program in Tokyo renders its storms as generative AI compositions. Even young children get it. Kindergarten teachers report 5-year-olds building chaos planets with glitter and fans, giggling as their creations spiral into beautiful messes no one could predict. What makes this educational revolution so potent is its timing. We're raising a generation that will grapple with Earth's own growing climate instability, where historical weather patterns no longer guarantee future safety. By studying a world where chaos is the baseline, students aren't just learning physics, they're developing a mindset. The next Einstein might not be the one who tames unpredictability, but the one who learns to dance with it, finding patterns in the storm where others see only noise. And HD 80606b, with its tantrums and triumphs, is the perfect partner for that dance, a reminder that sometimes the greatest discoveries lie not in the answers we find, but in the questions we learn to embrace. The chaotic ballet of HD 80606b's atmosphere isn't just rewriting astronomy textbook, it's quietly revolutionizing technology back on Earth. Those same equations struggling to predict the planet's supersonic storms are now being repurposed to tackle some of humanity's most unpredictable challenges. Take weather forecasting, where traditional models hit a wall beyond 10 days. By incorporating the hyper-chaotic principles observed on the exoplanet, researchers have developed algorithms that can trace how microscopic disturbances snowball into major events. The result, early warning systems that spotted the genesis of Hurricane Ida 48 hours sooner than conventional methods, giving coastal communities precious extra time to prepare. Disaster response teams are borrowing these cosmic insights too. When Mount Niragongo erupted in 2021, evacuation routes were optimized using traffic flow models inspired by HD 80606b's atmospheric currents, specifically how energy cascades through chaotic systems. The same math that explains why a tiny pressure change on the exoplanet triggers continent-sized storms now helps predict how panicked crowds might move during earthquakes or how wildfire embers could leap across neighborhoods. It's as if the planet's tantrums have become a training ground for crisis management, teaching us to expect the unexpected. Perhaps most surprisingly, Wall Street has taken notice. Quantitative analysts at major hedge funds now feed exoplanet chaos models into their trading algorithms. The logic is startlingly simple. If traditional economics assumes rational actors and predictable markets, HD 80606b proves that even physics-defying systems have underlying patterns, just not the ones we're used to. During the GameStop stock frenzy of 2021, funds using these adapted models detected the nonlinear momentum shifts hours before conventional tools, turning potential losses into gains. The same turbulence that scrambles a distant world's jet streams is helping traders navigate the equally volatile seas of high-frequency finance. Even healthcare is benefiting. Epidemiologists fighting COVID-19 unpredictable waves discovered that the planet's atmospheric reset points, moments when its climate abruptly switches states, mirrored how pandemic curves would suddenly spike despite containment measures. By applying chaos theory refined through exoplanet research, teams could identify hidden tipping points where small interventions might disproportionately flatten curves. A vaccination drive in Mumbai using these principles reached herd immunity 3 weeks faster than projected, proving that space science can save lives in operating rooms as surely as in orbit. What makes these spin-offs so transformative isn't just their practicality, it's their philosophy. HD 80606b forces us to stop seeing chaos as noise to eliminate, but as a language to decode. Its storms whisper secrets about network crashes, supply chain disruptions, even creative breakthroughs, all systems where controlled unpredictability breeds resilience. The planet's greatest gift might not be in the equations it validates, but in the mindset it cultivates. That sometimes the key to progress isn't fighting chaos, but learning to surf its waves. The discovery of any life, no matter how resilient, clinging to existence on a world like HD 80606b, would force humanity to confront one of the most profound ethical dilemmas in science. Do we observe or do we intervene? Picture a hypothetical scenario where microbial life somehow thrives in the planet's upper atmosphere, riding the violent winds between brief pockets of stability. Even if these organisms were nothing more than extremophile bacteria, their very existence would challenge our assumptions about the sanctity of cosmic ecosystems. On one hand, studying them could unlock revolutionary insights into biology's limits, perhaps even revealing novel biochemistry that reshapes medicine or industry. But every probe we send, every sensor we deploy, risks contamination. A single Earth-born microbe hitching a ride on our spacecraft could outcompete native life, effectively committing accidental xenocide. This isn't just speculative fiction. We've faced scaled-down versions of this dilemma before. When NASA Cassini probe discovered potential hydrothermal activity on Saturn's moon Enceladus, scientists deliberately crashed the spacecraft into the planet rather than risk contaminating a potentially habitable environment. That decision was made for a moon with relatively stable conditions. Now imagine the stakes on a world where the environment itself is a moving target. HD 80606b's chaos adds layers of complexity. would introducing even minimal human-made disturbances trigger unforeseen chain reactions in an already hypersensitive system. Its atmosphere behaves like a house of cards in a hurricane. What if our curiosity becomes the gust that collapses it? Yet the counterargument is equally compelling. If life exists in such extreme chaos, wouldn't studying it be a moral imperative? Earth's own tardigrades, microscopic creatures that survive space vacuums and volcanic heat, have inspired breakthroughs in vaccine preservation and radiation shielding. An organism thriving in HD 80606b's ever-shifting hellscape might hold clues to curing diseases or adapting to climate change. Some ethicists argue that withholding such knowledge would be its own kind of harm, especially if the alternative is passive observation until the planet's natural volatility inevitably wipes its biosphere clean anyway. The debate echoes terrestrial conservation struggles, just amplified to cosmic scales. National parks enforce strict, leave no trace policies to protect fragile ecosystems, but we also intervene to save endangered species from extinction. Which framework applies light years away? The Outer Space Treaty of 1967 prohibits harmful contamination of celestial bodies, but it was drafted when exoplanets were theoretical. Modern astrobiologists are now drafting protocols for active preservation, methods to study alien life without cross-contamination, like using sterilized microdrones or quantum sensors that can analyze chemistry without physical contact. Perhaps the most unsettling question isn't whether we can avoid interference, but whether we should. If HD 80606b's hypothetical life is locked in a perpetual struggle for survival against its own environment, would intervention to stabilize its climate be an act of compassion or arrogance? Terraforming has long been a sci-fi trope, but the ethical lines blur when applied to a world where natural means constant catastrophe. Would we be playing God or merely leveling a playing field already tilted by cosmic violence? This tension between exploration and preservation will only grow as telescopes uncover more chaotic worlds. HD 80606b might be lifeless, but it's a prototype for planets where the very definition of habitable stretches beyond our comfort zone. Its storms force us to confront an uncomfortable truth. The universe doesn't care about our ethical frameworks. Life, if it exists in such turmoil, will persist or perish regardless of our philosophies. Our responsibility isn't to nature's indifference, it's to our own conscience as the first species capable of asking these questions while reaching for the stars. HD 80606b has stormed its way into our collective imagination, becoming more than just a scientific curiosity. It's a cultural icon of cosmic anarchy. Scroll through social media and you'll find memes comparing its violent weather to Monday mornings, with captions like, "When you forget your umbrella on HD 80606b," over images of shredded umbrellas in hurricane winds. The planet's infamy has even spawned a viral hashtag, #ChaosPlanet, where users share absurdly unpredictable events in their lives alongside telescopic footage of the world's supersonic storms. This playful appropriation speaks volumes about how we process the incomprehensible, by turning astrophysical extremes into relatable, darkly comic relief. The planet's influence stretches far beyond internet jokes. Experimental musicians have transformed its erratic climate data into soundscapes, mapping temperature fluctuations to dissonant synth waves and hurricane winds to pounding percussion. One avant-garde collective, Orbital Resonance, created an entire album by sonifying the planet's atmospheric pressure changes over a single orbit. The result: a haunting, unpredictable composition that swings between eerie calm and ear-shattering crescendos, a sonic metaphor for the universe's indifference to human notions of order. Even Hollywood has taken notice, with sci-fi screenwriters using HD 80606b as shorthand for uninhabitable hellscape in scripts, replacing the tired trope of lava planets with something far more scientifically terrifying, a world where the sky itself is the antagonist. This cultural absorption reveals a deeper truth about our relationship with cosmic chaos. For generations, space was depicted as either sterile and orderly or fantastically alien. But HD 80606b bridges that gap. It's both rigorously real and unimaginably strange. Video game designers now consult astrophysicists to recreate its storms in alien worlds, while fashion designers drape models in swirling fabrics inspired by its infrared weather maps. Planet has become a canvas for our anxieties about climate change, AI unpredictability, and societal instability, reflecting back our fears through the lens of astrophysics. Perhaps most telling is how the scientific community has embraced this cultural dialogue. Researchers now sprinkle pop culture references into conference presentations, showing memes alongside data plots to illustrate complex concepts. When a major observatory released time-lapse footage of the planet's atmosphere convulsing, they cheekily titled the video "Interstellar Mood Swings," a nod to its internet fame. This synergy between hard science and mainstream culture isn't just about outreach. It's a recognition that wonder and humor are valid ways to grapple with the universe's most bewildering phenomena. After all, if a world 15 light-years away can make us laugh, shudder, and create art, maybe chaos isn't so alien after all, just humanity's newest muse in the endless quest to understand the stars. HD 80606b may be the chaos champion we know today, but it's likely just the opening act in a cosmic drama of disorder. Astronomers are already spotting other worlds that make this planetary rebel look almost tame gas giants with orbits so erratic they defy classification. Ice planets where entire hemispheres flash melt in hours, and rogue worlds tumbling through space with climates that reset like shuffled decks. Each new discovery chips away at our tidy definitions of what planetary systems should look like, hinting that hyper-chaos isn't an exception. It might be the universe's default setting for many worlds. The term hyperchaos itself is evolving from speculative jargon into a serious scientific framework. Traditional chaos theory deals with systems sensitive to initial conditions, like how Earth's weather can shift dramatically from tiny atmospheric changes. Hyperchaos, by contrast, describes systems where unpredictability compounds exponentially, where even the act of observation alters outcomes beyond recovery. Imagine trying to predict a pinball's path, not just in a machine with bumpers, but where the entire playfield warps in real time based on the ball's movement. That's the level of complexity some researchers now suspect governs planets like HD 80606b, where atmospheric disturbances don't just create storms, they rewrite the very rules governing how storms form. What makes this frontier so electrifying is how it's forcing entirely new mathematical tools into existence. When Dr. Amara Singh at Caltech recently modeled one such world's atmosphere using modified string theory equations normally reserved for quantum physics, her simulations suddenly aligned with telescopic data that had baffled conventional models. It was like discovering algebra could describe a rainbow, she remarked. Other teams are experimenting with machine learning algorithms trained not to predict specific outcomes, but to map the boundaries of unpredictability itself, essentially teaching computers to recognize when normal physics stops applying. The implications ripple far beyond exoplanet studies. If hyperchaotic systems prove common, it could explain long-standing mysteries closer to home, like why Jupiter's Great Red Spot stubbornly persists while other storms dissipate, or why certain solar flares erupt with no detectable trigger. Even Earth's climate history, with its sudden ice ages and warming periods, might reveal new patterns when viewed through this lens. Some astrobiologists speculate that life itself may be a hyper-chaotic phenomenon, with evolutionary leaps occurring not gradually, but in explosive bursts when genetic instability crosses hidden thresholds. The next decade of telescope launches promises to flood researchers with more chaotic worlds than they can currently explain. NASA's Habitable Worlds Observatory, slated for the 2030s, will scan hundreds of exoplanet atmospheres in unprecedented detail, while next-generation spectrographs like Andes will dissect their chemical fingerprints. Every instrument adds pieces to the puzzle, but the emerging picture is clear. The cosmos thrives on controlled anarchy. From the quantum foam to galactic superclusters, turbulence isn't noise, it's the engine of complexity. Perhaps the most humbling realization is how much we've underestimated nature's inventiveness. For centuries, we sought orderly orbits and stable climates as prerequisites for significance. Now, worlds like HD 80606b whisper a different truth: that the universe's most profound lessons often wear the disguise of bedlam. As we stand on the brink of this new understanding, one thing is certain: the planets we once called chaotic were never misbehaving. We just didn't speak their language yet. Ever wanted to conduct your own cosmic weather experiment without a multi-million-dollar telescope? Thanks to interactive online simulators, you can now tinker with HD 80606b's apocalyptic atmosphere from your laptop. No lab coat required. These digital playgrounds, crafted by astrophysics labs and universities, recreate the planet's violent climate in startling detail. Slide a virtual control to nudge its orbital eccentricity just 1%, and watch the screen erupt in storms that weren't there seconds ago. Crank up atmospheric metal content, and suddenly jet streams twist into braids of supersonic chaos. It's like having a god complex, but backed by real orbital mechanics. These tools aren't just for kicks, they're stealthy educators. By letting users manipulate variables scientists can't control in nature, the simulators reveal hidden cause and effect chains. One popular model, developed by the University of Chicago, starts with a simplified version of Earth's climate, then gradually introduces HD 80606b's extremes. Participants quickly learn why our planet's gentle breezes don't spiral into planetary hurricanes. Earth has oceans to absorb heat and mountains to disrupt wind patterns. Remove those buffers as the simulator demonstrates, and suddenly you're staring at a world where clouds move faster than bullets. What makes these platforms revolutionary is their accidental artistry. Watching a simulated storm split into twin vortices, only to merge hours later like celestial ballet dancers, exposes a hidden elegance in the chaos. High school teachers report students obsessively tweaking parameters, not to pass a quiz, but to create the most visually stunning atmospheric apocalypse. They'll spend hours engineering the perfect hypercane, says one educator, then realize they've accidentally recreated a storm pattern from last month's telescopic data. It's science disguised as a video game where high scores are measured in millibar pressure swings. Beyond classrooms, these simulators are quietly reshaping public science literacy. When a viral Reddit thread challenged users to stabilize the planet's climate, amateur climatologists proposed solutions ranging from artificial magnetic fields to orbital mirrors, most failing spectacularly. But a few stumbling onto concepts pros are now testing in pared-down models. That's the magic of democratized chaos. Sometimes the freshest eyes spot what specialists miss. After all, the equations governing HD 80606b's tantrums don't care if you're a tenured professor or a teenager with a smartphone. They'll defy anyone equally. The simulators also spotlight a profound irony. While we can't predict the planet's real weather, these digital sandboxes prove its chaos isn't random, just staggeringly sensitive. Tweaking one variable might spawn a storm that lasts centuries, while another almost identical adjustment leaves skies eerily calm. That paradox, predictable unpredictability, is the heart of modern chaos theory, and playing with it firsthand makes abstract concepts visceral. You don't just learn about the butterfly effect, you feel it in your gut when a 0.1% humidity change triggers a pixelated apocalypse. For researchers, these tools serve another purpose: crowdsourcing intuition. When a simulation player stumbles onto an atmospheric configuration that matches real telescopic data, it's like finding a needle in a haystack nobody knew existed. One grad student's idle experiment with methane concentrations recently explained why the planet's northern hemisphere sometimes cools while its star scorches it, a phenomenon that had puzzled scientists for years. In that sense, HD 80606B's online playgrounds aren't just teaching tools, they're collaborative labs where curiosity fuels discovery, one chaotic experiment at a time. The ultimate lesson these simulators offer isn't about planets at all, it's about perspective. Spending 10 minutes trying to fix HD 80606B's climate leaves players with humbling respect for Earth's delicate balance. Our atmosphere isn't boring, it's a tightrope walk over an abyss of possible catastrophes, stabilized by eons of fine-tuning. So next time you complain about a rainy forecast, remember, on a world where storms materialize like pop-up ads, predictability is the rarest luxury of all. Dr. Elena Park, an astrophysicist at Caltech who spent 12 years studying HD 80606B, leans forward with a glint in her eye when she calls it the most beautifully unruly object in our celestial catalogue. Her team's breakthrough came not from complex equations, but from a moment of sheer frustration. After weeks of supercomputer simulations failing to match telescopic data, one graduate student accidentally left a program running overnight with inverted temperature parameters. The next morning, they found the botched simulation had eerily replicated one of the planet's most baffling storms, a discovery that revealed how HD 80606B's atmosphere operates like a hall of mirrors, where even flawed assumptions can temporarily align with reality before the chaos resurfaces. Professor Javier Mendez from the University of Chicago takes a different approach. He sees the planet not as a problem to solve, but as the ultimate teacher. Chaos theory was abstract mathematics until this world gave it flesh and blood, he explains, pulling up a split-screen comparison. On one side, Edward Lawrence's original 1963 butterfly effect equations. On the other, infrared scans showing how 1,000 square mile temperature fluctuation on HD 80606B ballooned into a hemisphere-wide cataclysm in 18 hours flat. The patterns match with chilling precision, not in their outcomes, but in their fractal signatures of unpredictability. Mendez's lab now uses these parallels to train AI systems, feeding them exoplanet data to improve Earth's own climate models. Then there's Dr. Aisha Chen's radical perspective. The MIT researcher made waves by proposing that HD 80606B isn't truly chaotic. We're just measuring it wrong. Imagine describing a fireworks display using only a thermometer. She laughs. Her team's work focuses on hidden variables, potential forces we haven't yet imagined, like quantum weather effects or dark matter interactions that could explain the planet's capriciousness. While controversial, her approach has already yielded practical insights. New atmospheric sensors deployed on Earth's weather satellites, originally designed to hunt for her hypothetical exoplanet phenomena, are now detecting previously invisible microturbulences in our own jet streams. What unites these researchers isn't answers, but a shared sense of wonder. Dr. Park recounts the night her team first witnessed the planet's Great Reset, a fleeting moment when its frenetic atmosphere briefly stabilized into perfect bands before disintegrating again. "We all just sat there, staring at the screen like kids who'd seen magic," she recalls. For Mendez, the revelation came when his models unexpectedly replicated a storm pattern observed 7 years earlier, proving that beneath the apparent randomness, there were ghosts of order. Even skeptical Dr. Chen admits the planet's defiance humbles her daily. "It's like wrestling with an invisible giant," she says. "You think you've got a grip, then it tosses you across the room." Their stories reveal science at its most human, not a march of steady progress, but a series of stumbles, eureka moments, and humbling setbacks. When HD 80606b was discovered, astronomers assumed better telescopes would quickly explain its tantrums. Instead, each new observation peeled back another layer of mystery, proving how much we still don't understand about the fabric of reality. As Park puts it while zooming in on a real-time feed of the planet's latest storm, this isn't just teaching us about one world. It's showing us how to ask better questions about everything. So what's really driving HD 80606b's relentless chaos? Scientists have their theories: the extreme orbit, the metallic atmosphere, the lack of stabilizing oceans. But here's the thing: the universe loves throwing curveballs. Maybe there's more to this planet's tantrums than we've even considered. Picture this: what if its star isn't just a passive backdrop, but an active conspirator? Some researchers speculate the star's magnetic field could be interacting with the planet's own in ways we can't yet measure, twisting its atmosphere like a cosmic kaleidoscope. Or consider the possibility of hidden moons, not the serene kind we know, but rogue gravitational puppeteers stirring the pot with every close pass. Then there's the wild card of chemistry. We assume the planet's atmosphere is a predictable mix of hydrogen and helium, but what if it's laced with exotic elements we've never seen in our solar system? Compounds that behave unpredictably under extreme heat and pressure, triggering chain reactions our models don't account for. Some lab experiments on Earth suggest certain superheated metals can form temporary structures like atmospheric scaffolding that collapses without warning. Could that explain why storms vanish as suddenly as they appear? But here's where you come in. Some of history's biggest breakthroughs started as hunches from outside the ivory tower. Kepler's laws of planetary motion grew from his obsession with musical harmonies. The structure of benzene was dreamed up in a chemist's daydream about snakes biting their tails. So what's your take? Maybe you've worked with chaotic systems in unexpected ways, a meteorologist spotting parallels in ocean currents, a gamer recognizing patterns in procedural generation, or even a chef who's seen how sauces split unpredictably under heat. The universe doesn't care where good ideas come from. That's the beauty of a mystery this vast. Every time we think we've pinned HD 80606b down, it wriggles free, reminding us that discovery isn't a straight path. It's a collaboration between researchers with supercomputers, artists visualizing the unseen, and curious minds tossing around what-ifs over coffee. So whether you think the answer lies in undiscovered physics, interstellar weather patterns, or something nobody's dreamed up yet, drop your thoughts below. After all, the next big clue might not come from a telescope, but from someone watching this video. HD 80606b isn't just another exoplanet, it's a cosmic wake-up call. This turbulent world has done more than shatter our assumptions. It's rewritten how we see the universe itself. What began as a puzzling entry in telescope logs became a revelation. Chaos isn't the exception in the cosmos, but the rule. From the swirling storms of gas giants to the quantum fluctuations inside atoms, unpredictability is woven into the fabric of reality. And this planet, with its supersonic winds and explosive temperature swings, is our most vivid teacher. Consider how its influence ripples across disciplines. Climate scientists once viewed Earth's weather as the gold standard for atmospheric modeling, until HD 80606b showed them what true chaos looks like. Now, researchers scrutinize our own climate extremes with fresh eyes, recognizing the delicate balance that keeps Earth's turbulence in check. Artists and musicians, too, have found inspiration in its storms, translating raw data into symphonies and paintings that capture the beauty of disorder. Even philosophers grapple with its implications, debating whether unpredictability is nature's way of keeping the universe creatively alive. But perhaps the most profound lesson lies in humility. For centuries, humanity chased the dream of total predictability, from Laplace's demon to modern supercomputers. This distant world, spinning defiantly in the void, reminds us that some mysteries resist solutions. Its storms aren't problems to be solved, but phenomena to be witnessed, each a brushstroke in a masterpiece too vast for any single equation. That realization isn't discouragement, it's liberation. The universe isn't a clockwork machine. It's a living, breathing entity that thrives on controlled anarchy. As our telescopes grow sharper and our probes venture farther, we'll undoubtedly find more cosmic rebels, worlds that laugh at our models, stars that defy our classifications. HD 80606b is just the beginning. Its legacy isn't in the data points or research papers, but in how it reshaped our cosmic perspective. Disorder isn't noise to be filtered out. It's the universe's mother tongue, spoken in the birth cries of nebulae and the death spirals of black holes. So the next time you gaze at the night sky, remember, those twinkling lights aren't just distant suns. They're reminders that chaos and wonder are two sides of the same coin. And if you've enjoyed this journey to one of space's most unruly destinations, hit that like button, subscribe for more cosmic adventures, and let us know in the comments what celestial mystery should we unravel next. The universe is vast, unpredictable, and waiting to surprise us. Let's explore it together.